All right, here we are again, chapter 2. This will be the third installment on this chapter. This is hopefully a lot of the material in this chapter you've already have been exposed to or covered. So the very first thing we're going to talk about is water and the phenomenon of pH. And I like to refer to pH, and it has lots of different designations the way people discuss it, but I like to look at it as a percent hydrogen in the concentration of water. And that comes from the fact that, and I'm simplifying it, we have non ionized water, or we can have spontaneously form hydrogen ion and hydroxide ion. We know what those are. Remember that it's easier to lose an electron perhaps or gain an electron depending on the relationship. So pure water, if you were to take just pure water and it has equal amounts of hydrogen and hydroxide ions, then we would have a pH of 7. And that's right in the middle. It's ideal in the center. But really, when you think of pH, it's all about the concentration of the of hydrogen, the ions that are in the water, and the inverse proportion to that. In other words, if you have 70% hydrogen, then you would have 30% hydroxide ions, and so that would be a particular pH. And if you had that hydrogen percentage, so let me show you what I'm talking about. So the amount of hydrogen ions in a solution is the measurement of the acidity, and it's called the pH. So we have pH is 7, water. I told you if you disassociate water, pure water, with hydrogen and hydroxide, they'd be equal concentration, and we call that pH 7. And as the concentration of the hydrogen ion increases, or the percentage of hydroxide, the OH ion, decreases, the lower the pH down to 0. Now, stomach acid is around 2 something, 2.3 or something like that. But the hydrogen ions are very reactive. Strong acids are corrosive. Acids break down food in your digestive tract, so that's why that is what it is. And of course, we have mucus linings on our stomachs as a barrier to protect our tissues and the things like that. And acids are generally sour in taste. So as we go down the pH, the lower the pH, the concentration of hydrogen increases. And the opposite or a corollary to that, as you decrease the hydrogen concentration, the hydrogen ion concentration, and increase the hydroxide ion concentration, the higher the pH and more basic it becomes, and up to 14. And there's ammonia and bleach, and you can see that's pretty basic. So the hydroxide ion binds with the hydrogen ions, neutralizing acids. Strong bases are caustic to your skin. In other words, it can damage your skin readily. Bases can be found in many household cleaners. Bases are generally bitter in taste, and they're very slippery. If you've ever held some of these, like ammonia and bleach and things like that. So that's the basic relationship between acids and bases. So always think of an acid as the higher concentration of the hydrogen, and bases are more of the higher concentration of hydroxide. It's inverse relationship with each other. And so acids pH lower than 7 have a higher concentration of hydrogen than the hydroxide ion, can donate hydrogens to other chemicals. It's very reactive as a result of that. And good examples are stomach acids. Bases, pH that are higher than 7, they have a higher concentration of the hydroxide ion than the hydrogen ion. They have a bitter, slippery, soapy feel. Neutralizes acids to binding hydrogen to the OH, so this forms water. And acids will do this. Baking soda, bleach, milk, or magnesia, that sort of thing are examples of bases. So I hope that makes sense to you because I'm going to continue. Now, blood pH. The blood pH in our body is a normal one. We have to have a blood pH somewhere in about the 7.4 range, uh, and that's important. So we have buffers. We have ways to maintain that blood pH. It's so important. If you deviate by about 0.3 or 0.4, it's not compatible with life. And that's usually when the doctor says, I'm sorry, we lost your loved one because multiple organ failure. Well, we're going to talk about why pH is so important and why this is the case. But for right now, let's understand the purpose of and function of buffers. Buffers can quickly absorb excess hydrogen ions to keep solution from becoming too acidic. In other words, it buffers the amount of that hydrogen concentration so it maintains whatever that concentration was initially as best it can until it reaches its buffering capacity where it no longer can do that. So you have to understand some of the chemistry, and they can quickly release hydrogen ions to counteract any increases in the hydroxyl concentration. So buffers can absorb or it can release depending on the chemistry that's changing or trying to change the pH. So for an example, when blood pH level becomes too acidic, the buffer absorbs the excess hydrogens and the blood pH returns normal to the 7.4. When blood pH becomes too basic, or you have metabolic alkalosis, buffer releases hydrogen ions. So what you're trying to do is counteract some of the hydroxyl ions, and it forms water, and it returns the pH back to 7.4. So the buffers either absorb or they release hydrogens as it's needed to maintain. That's why I look at it as percent hydrogen, because really it always comes down to the hydrogen concentration, because the hydroxide ion concentration is always inversely proportional. So again, 50-50 or 70-30, however you want to look at it, it's that proportion. So and a proportion of what is the hydrogen ions and hydroxide ions as a result of ionized water that's have the hydroxyl group and the hydrogen ion as we see in water, and we've talked about that. So the amount of hydrogen or hydroxide ions in a fluid gives it really important properties. A particular amount of the concentration of the hydrogen ion in solution is a measure of its acidity. So I'm kind of rephrasing everything I've talked about, and we call this pH. More free hydrogen ions floating around. The D got clapped by the graphic here. I need to fix that. The more acidic the solution is. Pure water in the middle of the pH scale with a pH of 7. So any fluid with a pH below 7 has more ions and fewer hydroxide ions and is considered an acid. Any fluid with pH above 7 has fewer hydroxide ions and more hydroxyl ions and is considered a base. And you can see the measurement. Oddly enough, this swing from 0 to 14 is sort of a result of the way we measure. We can actually measure the charge of the hydrogen, the positive charge, with a voltmeter. And usually the analog voltmeters in the day when they were doing this was scaled to a range of 0 to 14. And I don't know if there's other explanations, but this is what I was told when I was in school, that it's that relationship to the old measurements of charge in the analog meters, the voltmeters, and that's why we have that range from 0 to 14. It's somewhat arbitrary, but again, it's the standard. It's what we use. And let me simplify. So the percent hydrogen, if we have 100% hydrogen, it's a 0, pH 0, and we have 0% of the hydroxide ion. At pH 7, we have 50-50. It's a mix. You see, it's inversely proportional. So if we have 50 of the hydrogen ion, then we have 50% of the hydroxide ion. The corollary to that at the base, if we have 14, which is way at the end of the scale, we have 0% hydrogen and 100% of the hydroxide ion there. So you can see that relationship is percent hydrogen. If you look just at the red part of here, you can see 100% is acid, 0% hydrogen is base, and that's why I like to look at it as a percent of hydrogen. So in the pH scale, you can see the various common things we've already talked about. But again, we have water dissociating spontaneously into the hydrogen ion and hydroxide ion. Now, I simplified it. In chemistry, they look at it a little bit differently, and but for our purposes here, let's go with this. If you go into chemistry with this background, you're going to do fine because the relationship, if you look at logs, and if you are familiar with logarithmic, it's the spacing of each of the individual measurements within a period of 10. So at pH 0, we have 1 mole per liter of hydrogen ions. So that is sort of the standard. And so the moles per liter of hydroxide would be 10 to the minus 14th. That's pretty small. That's really, really, really small. It's 0.00 with 14 of those zeros, well, 13 of the zeros plus a 1 to give you the minus 14. So that's a pretty small number. And so that's designated as pH. So the pH actually represents a range of discharge within each step. So pH 1 is 0.1 moles per liter of hydrogen ions. And that's what you're going to learn in chemistry, and there's more logic behind it. But for our purposes, we'll just keep with the basic relationship of the concentration of the hydrogen ions. So hydrogen ions are very reactive. Acids donate the hydrogens to other chemicals, and stomach acid is a good example. Hydrogen chloride, HCl, is a strong acid, and if you note, because the hydrogen dissociates from the chlorine, hydrochloric acid will break down into those, and single arrow goes in one direction, you see. So HCl in water dissociates, and that free hydrogen ions are there to ionize and change the pH. Bases, on the other hand, low hydrogen concentration but very high in the hydroxyl, and NaOH, sodium hydroxide, is a very strong base, and it dissociates into the hydrogen ion and into sodium and hydroxide, and so that OH group here is what does the trick as far as making it more of a base. And so a lot of times we have things that try to manage a particular pH as a buffer, as we've talked about. It will try to maintain that. So really, if we can just constantly think of pH is 100% at that concentration of the hydrogen ions at 0, and the corollary is at 14, the strong base, it's 0, and all the iterations in between. And pH 7, neutral, is 50-50. If you get that, I feel really good that you got the blood pH down. And again, just to review, the blood pH is really, really important to maintain. If you get the acidosis or alkalosis, depending on condition, your bodies have two different ways to deal with this, and we have some chemistry dealing with breathing and kidneys and the like that try to maintain this balance. And so the buffers quickly absorb excess hydrogens. The idea is you're maintaining that concentration of that hydrogen, because if you don't, then bad things happen. So blood pH levels change. If you can see, at 7.45, somewhere in between those ranges, and if we go up by about 0.4, really that's not compatible with life. You have a couple hours to try to pull the patient out of that, but if it gets worse and sustained, then it changes the shape of very important types of proteins. We're going to talk about what proteins are, but because of the pH, it changes the characteristics and they no longer function. So if it's a protein that contributes to your breathing center, so you breathe, and it changes its shape because of a change in pH, then it can no longer function that way. Bad news, unfortunately. So buffers resist change in pH. If you can remember that, that's the key point. Chemicals that serve as a buffer can absorb hydrogen ions and in solution becoming too acidic, and they can quickly release them. And so the ions counteract any increase in the hydroxyl concentration. So I told you it's that inverse proportion. Buffering capacity is to measure how well the buffer resists the change. In other words, at some point, you're going to overwhelm the buffer and it no longer works. And that's what that is at that point. And that's how much buffering capacity we talk about. So here's a real world blood pH and buffers. Two solutions, A and B. Solution of 0.2 molar hydrochloric acid and a solution of 0.2 molar sodium hydroxide and a pH meter to measure the pH. The experiment of one, you're adding it has a pH of measured pH is pH of 1, and then after you add a sodium hydroxide you get pH of 12, and then if you add hydrogen chloride HCl in solution B and balance it, you can change the pH by adding these components until you balance it to get the pH that you're after. So the buffering capacity and being able to control the solution. So that's the point of this diagram. Solution A, the buffering capacity is lousy. You add 10 ml of HCl, the pH goes to 1. You add 10 ml of sodium hydroxide, the pH goes to 12. You see, we're in a buffered you can add 10 ml of HCl and the pH changes from 7 to 6.8, and you add sodium hydroxide to the solution. So the buffering between these two, this has got much more of a buffering capacity than solution A. Now solution A would behave like a lake or stream, and acid rain would change that pH of that lake very quickly, and because it's just regular stream water or lake water, poorly buffered, and it changes pH and will kill life as a result. So if you had a buffered system like our blood, and then having these increases for whatever reason, we can buffer it and handle it by changing the concentration, that either absorbing or extruding the hydrogen ion into the solution from the buffer. So that's really what I was trying to explain. So our observation from this experiment, that solution A underwent drastic changes in pH upon the addition of a strong acid or strong base, while solution B resisted that change, and that's due to the buffering capacity. So that is the summary. The pH of a fluid is measured by how acidic or basic a solution is. It's dependent on the concentration of the hydrogen ions, and we know that. And the lower the pH, the more acidic the solution. Acids such as vinegar can donate protons, that's just another name for hydrogen ions, to other chemicals, while bases including baking soda bind with free protons or hydrogen ions. Buffers react to resist this change in pH. So if you remember that, I'll be very pleased. We use antacids as a way of adding additional buffering system to our stomach and stomach acidic environment using a particular antacid. You can evaluate it by the effectiveness of protein digestion enzymes at different levels of acidity. And in other words, the protein would change its shape, this digestin enzyme. So if it changed its shape, from its optimal shape to a less optimal than its activity. We're going to talk about what enzymes do and how they work, and I'm just sort of an introduction. As you change the shape of the enzyme, it no longer functions to normal, and its ability to do whatever, in this case digesting, starts to decrease. Second, they observed 152 people who were seeking treatment for an ulcer, which is have a huge amount of acid production that actually burns a hole. In other words, the lining that's there, the mucus lining, is no longer really functioning very well, and you start to basically break down your own stomach intestinal lining, and that's called an ulcer. So after a 3-month antacid treatment, signs for allergic reactions to a variety of proteins were done in this study. So a typical stomach of pH 2, proteins in milk are completely digested 1 minute. At less than pH a value of 3 or 5, the milk proteins were largely undigested. So the enzyme that breaks down the milk protein doesn't work as well at 3 to 5 value of pH. So it's sensitive to the amount, the concentration of the hydroxide ion, or the less of the hydrogen ion, and it changed the shape of that protein, so it doesn't work as much. And don't worry if you don't get this now. I love introducing these early, and it gives you a chance to kind of think about it. But with 3-month antacid treatment, 10% of the subjects exhibited signs of having had an immune response to at least one of the 19 dietary proteins. 10% of the control group exhibited the same. So after 3 months of antacid treatment, 26% of subjects exhibited signs of having immune response. So it changes the ability of the protein. So to be recognized by the immune system. The researchers concluded that antacids hamper the biological gatekeeping function of the stomach, and as their conclusion is supported by the data. Not really. You'd have to do more work with this, and you can do searches if you want with Google Scholar to actually find the study. If you're interested in this, the cause and effect relationship between antacids and allergic responses was it demonstrated? And I would say not. You would have to have more information about that and why the biological function is changing because of the pH environment and the shape or the activity of that enzyme. So you would just plan more experiments along the way, is what we would want to do. Dietary proteins are not digested as well in the stomach. pH is increased as a result of medications taken to treat ulcers, heartburn, and other. This can put people that take antacid medications at risk for developing allergic responses to common foods. And this is a trend, and I love bringing these things up because this applies things that we're talking about to real world. And I don't know if you've ever experienced a food allergy, but it's not fun. And having an immune response, and we're going to talk about that. But again, antacids also decrease your ability to digest food, and having indigestion as a result of that is also bad. So it's a give and take, and that's always the case. But I wanted to give an example of something that talks about the pH. Now, we're going to talk about proteins and shape, structure, and function later on, so don't worry about that now. Just know that pH changes and has these effects, and we'll talk more about those as we move on. All right, that concludes Chapter 2. I hope you enjoyed this section. There are some assignments. If you could work on those, so you just go in that peruse the folder there, and that'll be that. I'll talk to you when we move on to our next chapter.